So we're going to talk about limits of human reasoning, limits of mathematical reasoning in this lecture. And it's going to be kind of like a corollary to what we have seen so far in the last week of the course. And it's really, really cool that we can actually say something about this human process of mathematical reasoning and say something rigorous about it and actually show some interesting properties about it. Let me start by reminding you last time what we did. We diagonalized against a set of all decidable languages to show that the complement of self-accepts, or in other words, SA bar is undecidable. And we used reductions to show other problems are undecidable as well. We reduced the complement of self-accepts to self-accepts, which shows that self-accepts is undecidable. We reduce self-accepts to accepts, which shows accepts is undecidable. We reduce accepts to halts, which shows halts is undecidable. We reduce halts to sat, which shows sat is undecidable. Okay, so now we've completed formally defining computation. Turing machine is our model of computation. We are understanding the limits of computation. And now we're going to be looking at, as a corollary, we're going to be able to understand and say something very cool about mathematical reasoning itself. Cool. Okay, so what do we want to do? So let me remind you this concept that I introduced in lecture 1.5, good old regular mathematics. Good old regular mathematics is the mathematics that we've been doing for centuries. I'm going to denote this by GORM, right? And GORM is pretty awesome because whenever you have something you want to understand, right, something of interest that you want to understand better, our best, in some sense, strategy, our best method to create reliable explanations, create reliable knowledge, is this picture, okay? So we create a mathematical model that hopefully faithfully captures what we're interested in, and then we use logical deductions to create new knowledge in the mathematical world, and that translates back into new knowledge in the real world, okay? So that's kind of the hope. And this is the picture. For example, you want to understand gambling better, you want to make more money, you create a probability theory, you prove things about probability in the world of probability theory that hopefully allows you to make more money in gambling situations. You want to, you're interested in farming, you want to understand the areas of different shapes and angles and so on and so forth. Maybe that forces you to, invent plane geometry as a field. These abstract notions, create new knowledge, and hopefully there are some cool applications there, right? Now our goal, I told you, in lecture 1.5, in early 20th century, late 19th century, people started to realize that there are some fundamental gaps in mathematical reasoning itself. So it became clear that we needed to actually formalize mathematical reasoning itself, okay? So we're going to take this human process of mathematicians, people doing mathematics, proving theorems, and we want to understand this better. We want to put this on a solid foundation, right? And this is what I'm calling form. It's the formalization of good old regular mathematics, GORM, right? And so now the thing that we want to put under the microscope, the thing that we want to understand better, is mathematical reasoning itself. It's GORM itself. Okay? Now this makes things a bit, hard to digest and understand. There's this sort of circular nature to this. There's this mathematical reasoning, good old regular mathematics that we do here, and now we're taking this and we're putting this here as the thing that we want to understand better, and we want to now create a mathematical model for this human process that we call GORM, good old regular mathematics. Okay, so now if you want to do this, what do you need to do? So you think about the elements of good old regular mathematics. So you need to model. There are two steps to this, okay? So one is the modeling phase. You take this human process, and I want to come up with a precise mathematical definition that captures this. And once I have that, it's awesome. Then I can actually study it rigorously in this world and prove properties about it. So now we have to think about, okay, what are the elements of mathematical reasoning and what do we need to model? So, again, this is from lecture 1.5. I said, like, look, the basic elements of mathematical reasoning is that, there are these things called mathematical statements that have truth value. You have axioms, things that you assume to be true. There are deduction rules. There's a concept of a proof and a concept of truth. And somehow you want to sort of come up with a mathematical model for this, right? And, let me just briefly tell, again, you what these pieces are informally so that we're all on the same page. So a statement is just a well-formed sentence with a truth value. An axiom is an obviously true statement. We start our deductions from axioms so that we don't have infinite regress. A deduction rule is a rule allowing you to derive new true statements from previously established true statements. And a proof is a chain of deduction starting from the axioms and ending at the statement that you want to prove. And in this context, proof really is, in my view, equivalent to knowledge, right? So in the context of mathematics, when you say, how do you create new knowledge in mathematics? You create new knowledge in mathematics by proving new things, okay? And finally, the hope is that, truth corresponds to provability in your formalization, okay? So, of course, you want whatever you would hope, like the ideal is that whatever is true is provable in your system. And, of course, whatever is provable is hopefully true. You don't want to prove wrong things, right? So if we can come up with a satisfactory formalization of mathematics, our hope will be that provability is going to correspond to truth. Okay, so now there are two parts, as I said, of form, right? So one, you have to agree on, how do you represent the basic mathematical reasoning elements formally, okay? And once we do that, we can now say, okay, let's actually see like what we can prove about form and see what interesting things we can say. Now, the thing is, I'm actually, in terms of part one, I'm not going to tell you much. I'm going to tell you the bare minimum, the exact minimum that you need to understand what we will do in part two. Okay? And we will prove some very interesting things in part two, given we have some formalization of mathematics. But it turns out that you don't need to know much about the details of how mathematical reasoning is formalized to be able to do part two. You need to know just a little bit, and I'll tell you the bit that you need, and then we're going to move on, okay? Because this is not a class on how you formalize mathematics exactly, but we want to see how you do part two as actually corollaries of ideas that we have seen before. Okay, so what do you need to know about form? Okay, so it turns out the crucial aspect of form that is relevant, for us is that GORM is a computational process. Good old regular mathematics is what? Well, you have mathematicians engage in mathematical reasoning. Some mathematicians are trying to prove some statement, some mathematical statement S. So you have this person is a prover who wants to prove something. So P is a proof of S if it exists. And there's a verification process, which is very important. Okay, so given some statement S and some argument P, some proof P, the verifier needs to check, is this a valid proof of the statement S or not? Okay? And crucially, these are human processes, but these are computational processes. Okay? And once you realize that, a lot of things start falling into place nicely. First of all, you realize that, okay, when I want to formalize this thing, the way we formalize computation, we represent statements, these inputs to computation as finite length strings. So statements and proofs are going to be represented as finite length strings in our formalization. Okay? And we want the verification to be a decidable process. Okay, so I think we can all agree that whatever we call mathematical reasoning, we want that the verification process. If someone gives us a proof and some statement S, we should be able to actually efficiently decide whether that proof is actually a proof of S or not. Okay? Now, whether the prover, the first one, is efficiently decidable or decidable at all is open, right? So we don't know. Maybe it's not possible to do that. Maybe there's no algorithm that given a statement S is going to tell you what the proof is. We don't have that requirement, but definitely we have the requirement that verification, it has to be a decidable process, and it has to be an efficient decidable process. Efficiency in this lecture is not going to matter. I put this in parentheses because for our arguments it won't matter, but it is important that this should be this should be a decidable process verification. Now the first one, provability, like we can create a decision version of this process. So let me ask, like, is it provable or not? Given a statement S, is it provable or not? Now it's a yes/no question. And whether actually there is a decider for this or not is precisely, if you remember, Entscheidungs problem. Right? Hilbert asks us, like, given a mathematical statement, is it provable or not? Yes or no? Is precisely what Hilbert asks. He asks, like, is there an algorithm for this procedure or not? If there is, it would be awesome. But maybe there isn't. Maybe there is. We'll see. We'll try to make a conclusion about that. But yeah. OK, so here are now the key elements of formalization that you need to know. OK? So whatever formalization that we're using to formalize Gorm, we want the following things. One, that for every statement S in good old regular mathematics, I want a precise representation of that in my formalization form. Okay? And I'm going to denote that precise representation with this angle bracket S. Okay? It's a string representation of this mathematical statement S. I want that for every argument P in good old regular mathematics, there's a precise representation of that argument in my formalization of mathematics. And I'm going to denote that by angle bracket P. And I want that my formalization of mathematics, Gorm, specifies the verifier. Okay, specifies a decider Turing machine V called the verifier, such that this verifier takes two inputs, some statement and some argument, and will tell me, it will accept if and only if P is a correct proof of S. Okay. Now there's no like one formalization of mathematical reasoning. You can come up with different formalization of mathematical reasoning, just like you can come up with different formalization of algorithms and computation. You can use a Turing machine model, you can use a lambda calculus model, you can use something else, right? And here as well, form, it can have, there could be multiple good candidates for this. I am not going to care about which particular formalization that you use. All I care about that your formalization should satisfy these properties. Okay, and if you tell me this, then we are ready to go. We are ready to roll. Okay. So this might be surprising to you in one sense that, how am I going to be able to argue about and say something interesting about form without knowing the details of how these things are done? Right? You might say that. But let me ask you this. When we proved undecidability and the limits of computation, how much of knowledge of Turing machine was relevant to us? Did I really need to know that the Turing machine is a 7-tuple and has these states and the transition function and so on and so forth? If you think about it, I didn't really use those stuff at all. All I needed was that, Turing machine model captures faithfully what we understand at a high level as an algorithm, and my arguments were using high-level algorithms. And this is precisely what we're going to be doing here as well. Okay? I don't need to know the specific details of how you formalize mathematical reasoning. I just need something analogous to the Church-Turing thesis. Right? Really, when I showed undecidability, I really was appealing to Church-Turing thesis that, if I describe to you an algorithm in high-level English, you accept that there is a Turing machine that corresponds to that. Right? And so we need a similar thing here. Before I tell you that, though, let me just make a quick terminology, quick definition. We're going to say that S is provable if there exists some string W such that V, the verifier, given S and W accepts. So the verifier will recognize W as a proof of S. So this just means that there exists some proof for S. Okay, so this is the verify. Now, let me, before I tell you the Church-Turing thesis of mathematics, let me just make a quick observation here, which actually will be important for us. So, in this specification, I'm not saying like the form should specify a prover. And because the verifier is actually V is enough. And from the verifier, it turns out you can create a prover. Okay, so let V be the verifier. Then I claim that we can build a very natural prover from it. Okay, so maybe someone can see. Now, I don't claim, I'm not looking for an efficient prover. I don't care about efficiency in this lecture at all. For the results that I want to prove, efficiency will play no role. But can I build a prover given the verifier? It could be a very inefficient process. What's the natural thing to do? Yeah.
Check every string, and if it holds for every single string, like the statements holds for within its string.
Yeah, check every string is like brute force search, right? So here's what we're going to do. For k equals 1, 2, 3, for every string w of length k, I'm going to check, is w a proof of S? And if the verifier accepts, then, oh, I found a proof. I'm going to return the proof, w. It's a brute force search. So you can do this. Right? Now, is it efficient? No. Granted, it's not efficient. But nevertheless, it's a prover. And notice that if there exists a proof of S, if S is provable, this guy will find it. Eventually will find it and return it to you. Okay, so I can also write this as like solving or attempting to solve the decision version of it is provable. And in fact, I'm going to write this down because it's kind of important. Is this, let me come to this one. Is this a decider? At this point, we don't necessarily know it's a decider or not, right? So maybe it is the case that S is not provable, and the negation of S is not provable. So this might just keep going, right? If S is provable, though, does it return, find and return true? Does. So then it's not a decider, but it's what? It's a semi-decider. Okay, so we have a semi-decider for provability. It's now, right now, for as far as what we know right now, we don't know if it's decidable or not. We just know it's semi-decidable. Okay. Now let's ask this question. Is there an agreed upon form that we can work with? Just like, the Turing machine model is an agreed upon formalization of computation. Is there something similar for good old regular mathematics? And this brings me now to the Church-Turing thesis of mathematics. And I'm going to call this the Gorm to ZFC thesis. Okay? If you Google this, you won't find it. I made this up. But let me remind you the Church-Turing thesis. And the Church-Turing thesis says that the Turing machine model is the right model for an algorithm that we understand, right? So every algorithm that you can describe at a high level compiles down to a Turing machine eventually. Now, I'd like to describe, let me just describe the Church-Turing thesis as Gora to TM thesis. What does Gora mean? Gora means good old regular algorithms. Okay? So it's a Church-Turing thesis is really a good old regular algorithms to TM thesis. Okay, it's saying that good old regular algorithms, the correct mathematical model for it is the Turing machine model. And now I want the same thing for mathematics, and this is I'm going to call the Gorm to ZFC thesis. And this says there's a particular axiomatic proof system called the Zermelo-Frankel choice, ZFC for short, proof system, is the right model for Gorm. And what this means is that, I'm not specifying what ZFC is right now, and I won't actually, but what this means is that every Gorm statement has a corresponding ZFC statement, and every Gorm proof compiles down to or has a corresponding ZFC proof. I will not tell you what the ZFC axiomatic system is just because it's not relevant. What I need is this thesis. If you grant me this thesis, then we can move on and prove interesting things. Okay? Okay, so this thesis tells me that every high-level mathematical statement that I can write when we communicate to each other has a precise representation in this formal system. This is now the form that we're in the ZFC system. And every argument, every proof that I write, I do in 251, for example, has a corresponding formal proof in ZFC. Okay, so now we're happy with this. And that's it. That's it for part one. I don't want to say anything more. We don't need more than this. We need the Gorm to ZFC thesis, and we'll be good to go. Okay? Now, with that, we can prove interesting properties about form, and therefore Gorm. Okay? Now, let's ask the following question. What are some properties that you would want from any formalization of mathematics? I mean, I've already told you some of these things. Like for every statement, I want a precise representation. For every argument, I want to present precise representation. I need a verifier Turing machine. So then what do I want these things to satisfy?
You can't prove a statement and a negation.
Yeah, exactly. I mean, I implicitly said here when I was doing this, like I said, if, verifier finds a proof for the negation of S, hopefully then, there's no proof for S. That would be bad, right? You agree that if there's a proof of S and the negation of S, that's bad news. That's inconsistency. We don't want that. So that's good. That's one thing we want. What else do we want? Or we would hope, let's say. Ideally, what we would want. Consistency, soundness, and completeness. Consistency is, this is what we started with, for every statement S, at most one of S or the negation of S is provable. Obviously, we don't want both S and negation of S to be provable. If that happens, that's bad news. Don't use that system. Because if you don't have a consistent system, then it turns out that you can prove any statement. Why? Because here's, so suppose you have a system that is not consistent. So there is some statement S, such that S and the negation of S is provable, then I'm going to prove any other statement T that you want. So here's my proof for T. I want to prove T. I'm going to assume for the sake of contradiction the negation of T. I'm going to derive or prove S. I'm going to prove the negation of S, and I reach the contradiction. Therefore, T is true, or T is proved. Okay, so if you have inconsistency, it's completely useless. Okay. Now, then we talked about soundness, right? So we want that if S is provable, then it's true. Like we're proving true things. We don't want to prove false things, right? So false statements are not provable. This is equivalent. And here, one observation I'll make is that actually soundness is a stronger condition than consistency. If you have soundness, that implies consistency. Okay? If you have a sound system, then it has to be consistent. I mean, you can think of it from the contrapositive side. If it's not consistent, as we saw, we can prove any statement. So you're going to be proving false statements, and it's going to be unsound. Okay, soundness implies consistency. And finally, completeness would be great. For every statement S, at least one of S or the negation of S is provable. So this would be great to have. Okay? And in fact, the ideal situation is to have, I mean, we already said soundness implies consistency. The ideal situation is to have a sound and complete formalization. This is the dream, okay? And if this dream is realized, then the hope that truth corresponds to provability is achieved. Okay, so when you have a sound and complete system, you know that for every statement S, either S or the negation of S is provable, and you know by soundness, whichever is proven, it's true. So you get that truth corresponds exactly to provability. That's the dream. And this was Hilbert's dream. This was Hilbert's dream. And as I told you, he was a very influential mathematician at the time. He really accelerated the efforts to put mathematical reasoning on a solid foundation. And one way to capture this effort was, the Hilbert's program, what's known as Hilbert's program. Hilbert's program asks the following. It asks, formalize Gorm, come up with some formalization of Gorm. Prove that your formalization is complete, and prove that your formalization is consistent. Okay? And he really believed that this would be possible. Like he was like, prove these things. He thought that this would be possible. Now you might ask, why not prove soundness? Why is he talking about consistency and soundness? It's a bit of a subtle technical point, so I'm going to avoid. I'm going to leave it as a puzzle for you. Okay? But now the question is Hilbert's program achievable? Okay, so let's see whether any form with the properties that we described could be consistent and complete. Can we come up with a satisfactory formalization along the lines of what Hilbert is asking? Okay, and the punchline here is going to be the following. We're going to be able to show that Hilbert's stream is not achievable, and it will be basically a corollary of the work that we've done last week. I mean, the work of Cantor led to understanding our limits of computation, and our understanding of the limits of computation is going to directly allow us to conclude the limits of mathematical reasoning and limits of formalization of mathematics. And the simplest or the shortest way I can describe this implication is the following. Just think about it in terms of the contrapositive. We're going to be able to show that if you come up with a satisfactory form in the sense that Hilbert was asking for, then you can actually compute undecidable problems. Okay? That would allow you, a satisfactory form would allow you to compute undecidable problems. And since we can't decide undecidable problems, we can't get a satisfactory form. We cannot get a form which is both consistent and complete. Okay, so this will be our task now. This is what we're going to do. Okay, so here's the plan now. We're going to talk about zeroth incompleteness, first incompleteness, soundness version 1, soundness version 2, and there's a consistency version, and then the second incompleteness theorem. In literature, when you look at incompleteness theorems, they're referring to these ones, consistency version and the second incompleteness theorem. But I'm going to kind of warm up to it. And really the, philosophical, in some sense, punchline, the important part is really this one, first incompleteness theorem, soundness version number 1. The first one that we do is going to be like, is going to actually give us the take-home message anyway. And then the rest is kind of like bonus on top of it, cherry on the top. Now I'm going to start with zeroth incompleteness theorem, but before I do, let me give you the setting once more. Okay, so here's what we're working with. Okay, so we're going to be taking as our form the ZFC axiomatic system. Do we need to know the details of it? No, it doesn't matter. Here's what we need to know. We need to know that there's a Gorm to ZFC thesis, which tells us that for every Gorm statement and Gorm proof, there's a corresponding ZFC statement and ZFC proof. In this formalization, we have our verifier, which is a decider. Given some statement S and some argument P, the verifier will tell us whether it's a correct proof of S or not, accept or reject. Okay, and this is as I said, a decider. It always gives us the answer. And here's some terminology that we're going to be using. Once again, I'm going to say S is provable. This means that there's a proof of S in form, in the form that we're using. S is independent means neither S nor the negation of S is provable. And incompleteness means what? Incompleteness means that there exists some independent statement S. Right? So because completeness means that for every statement S, either S or the negation of S is provable. So if it's incomplete, there exists some statement S such that neither S nor the negation of S is provable. So there exists an independent statement, some statement which cannot be resolved. So now let's do it, okay? So let's start with the 0th incompleteness theorem. This is something that I made up again, okay? There's no, if you just Google 0th incompleteness theorem, you're not going to find anything. But it is something that I want to mention very briefly because, you know, it's good. It's a good realization. It's a good observation to make, I think, okay? And this observation is the following. Look, you know, there's a fundamental limit to mathematical reason. Before you even go into the incompleteness theorems of Godel, there is maybe a more fundamental limit that you should be aware of. And it's the following. Look, you know, we are Turing machines, okay? I'm a Turing machine, okay? So I can only take as input finite length string inputs. I can only produce finite length string outputs. When I do mathematics, it's a finite process. It's using finite, like my statements are finite. The proofs that I use are finite. On the other hand, the possible mathematical concepts out there, it's uncountable. They're not all. You cannot always encode a mathematical concept with a finite length string. The set of real numbers, for example, is an uncountably large set. So if you said like take an arbitrary real number with arbitrary random looking decimal places, there's no way to compress down this to a finite length string and communicate. Okay? Now you can talk about the set of all real numbers. That concept is finitely describable. You can talk about a number like pi. Pi also has a finite description. But not all real numbers have a finite description, right? So you know, I can only work with finitely describable mathematical concepts and objects. And I can only hope to reason about those things. So, yeah, we can't hope to reason about everything. Only the things that have finite description. You know, it's a good thing to realize. Okay, but now let's come to the real thing, okay? So, the first incompleteness theorem, soundness version. So here is what we want to do. We want to show that ZFC cannot be, or any formalization of mathematics that you have in mind, cannot be both sound and complete. And what did I tell you? How are we going to do this? We're going to say, look, if you have a satisfactory formalization of mathematics, that would allow you to compute the uncomputable. Right? So let's assume, for the sake of contradiction, that ZFC is both sound and complete. Then, as I told you before, then truth becomes equivalent to provability. Okay? Then what do I have then? What does it say about this guy here? So we said, in general, this is semi-decider. But if I'm in a situation where I have sound and complete system, then this becomes what? A decider for is provable, right? But at the same time, provability is equivalent to truth. So this becomes a decider for truth. Whoa, can you have a decider for truth? So now, what this implies is that we can then decide any truth. Right? So any statement you have, S, it's either true or false, right? If it's true, there exists a proof of S. If it's false, there exists a proof of the negation of S. My resolver here is going to find either the proof of S or the negation of S. And will tell you, oh, it's true or false correctly. And I know by soundness, I'm assuming soundness. Because I'm assuming soundness, whenever this guy returns true or false, it's giving me the correct answer.
So if you can put in any statement, can you present something like, I don't know, this Turing machine halts or something, and then just basically decide the undecidable?
Yes, exactly. That's exactly what I can do, right? So, if I have a truth oracle, basically what I'm telling you is I'm going to call this is true. This is like a truth oracle now. If I have a truth oracle, I can compute anything, right? Here, what you're saying halts, right? So given M and X, it's a one-liner. Who can tell me the one line? I'm going to use this as a helper function, obviously. Yeah?
Is true and then the encoding of the statement S
Yeah, exactly. Is true. M of x halts is a mathematical statement, right? I'm going to use it encoding of it in the formalization that I have. And then is true is going to tell me whether this is true or not. Wonderful. So you see, a sound and complete system is too good to be true. Like if you have a sound and complete system, you get a truth oracle. If you have a truth oracle, a computable truth oracle, you can compute anything. You can compute halts. It's not specific to halts, by the way. SAT, okay? Given a Turing machine M, is it satisfiable? Does there exist some string that the Turing machine accepts? One-liner. Return is true. There exists x such that M of x accepts. Okay, so I'm now solved that one. Here's my favorite undecidable problem. The complement of self accepts. One-liner. Return is true. M does not self-accept. Does not self-accept mean M, when given as input its own encoding, it does not accept. So let me pause here. This is the most important part. This is the most philosophically relevant thing here. Okay? A sound and complete system would be too good to be true. It would allow us to compute the uncomputable. And as you can see, the limits of form is a corollary of the limits of computation. Right? Because we are able to argue that these problems are not computable, we can say that you cannot get a sound and complete system. Good, so this is what we have. Our theorem is that ZFC cannot be both sound and complete. Why? If it's both sound and complete, then I can decide an undecidable problem like the complement of self-accepts using these two algorithms here. Very simple. So another way to say this is that if ZFC is sound, then it's incomplete. Okay? And we don't doubt the soundness of ZFC. Okay? You know, we assume, of course, we assume it's sound. If it's not sound, of course, we can't do anything with it. And assuming it's sound, then it must be incomplete. Okay, good. So now this is an existence result, right? So this is saying, another way to say this is that it's incomplete, which means that there exists some statement S which is independent of ZFC. Right? On the other hand, I have not specified for you what such a statement is. All I've shown you is that there exists some statement which is neither S nor the negation of S is provable. So it's independent. There exists some statement like that, but I haven't told you what, I haven't given you an explicit one. Okay? And the soundness version number 2 is all about that. Let's find an explicit statement which is unprovable. Now this is going to get a bit more tricky, okay? So we're going to have to work a bit harder here. So here's what we have, the situation. Assume ZFC is sound. What is an explicit statement S which is independent of ZFC? And here are the two algorithms that I have. So I have this algorithm that is supposed to decide the complement of self-accepts. Now I'm going to assume soundness. I'm not going to assume completeness now. I'm not assuming completeness. I'm assuming soundness though. Okay? And I know that the Turing machine that I wrote here is a perfectly valid Turing machine. Like this is a perfectly valid Turing machine. Nothing wrong with this. It's a perfectly valid Turing machine. And it is supposed to decide the complement of self-accepts, but we know it cannot decide the complement of self-accepts because it's undecidable. So this guy here is not a correct decider for the complement of self-accepts. It cannot be, of course, because complement of self-accepts is undecidable. Now, what does that mean? So if this is not correctly solving the complement of self-accepts, that means by definition that there exists some input such that this machine gives the wrong answer. Right? So for some input, which means for some Turing machine M, this guy doesn't give the right answer in attempting to solve the complement of self-accepts. Okay? Now, why doesn't this guy give the correct answer? This guy only calls resolve with this statement here, right? So this means that for some input M, for some Turing machine M, resolve does not give the correct answer. Right? So resolve, I'm just calling, it doesn't give the right answer. And there's only one way this can happen. Because I'm assuming soundness, what that means is that whenever this resolve returns true or false, it gives the correct answer. Soundness means that. But now there exists some Turing machine M such that resolve does not give the right answer. So that leaves one possibility. Yeah, so it loops forever. It never halts. It never gets to return true or false. That has to be the case. Okay? So resolve here doesn't give the right answer means that for resolve to not give the right answer, the only possibility is that it's looping forever for that input. Because whenever it returns true or false, it gives the right answer because of soundness, because we are assuming soundness. And that means that there exists some Turing machine such that M does not self-accept, is independent. Why would this loop forever? It's not able to find a proof of S, nor it's able to find a proof of the negation of S. So it just keeps going and going and going and going. And that means that this statement, M does not self-accept, is independent. Okay, so once again, here's a Turing machine M. It's supposed to decide the complement of self-accepts. But of course, the complement of self-accepts is undecidable. It cannot decide it. So what does that mean? It means that for some input, this Turing machine gives the wrong answer when trying to decide the complement of self-accepts. So for some input, so for some Turing machine, resolve does not give the right answer. And the only way resolve does not give the right answer is when it loops forever. Because if it halts and returns true or false, by soundness, it gives the correct answer, by the assumption of soundness. Okay? So the only way that it does not give the correct answer is because if it loops forever. And if it's looping forever for a certain statement, that statement is independent, right? If resolve loops forever for a certain statement S, that means that you're not able to find a proof of S or the negation of S, so it's independent. So now, if you're happy with this, of course, it's still an existential statement, right? I'm still saying, well, there exists some Turing machine M. So at least I know that for some Turing machine M, there is such a statement which is independent. I want to still nail down for you the precise Turing machine M, such that this statement is independent. Okay, so now that's what I want to do. I'm going to give you an explicit Turing machine M, such that M does not self-accept, is independent. So now for this, we're going to go back to our diagonalization argument. Okay, so how did I build the decision problem, the complement of self-accepts? I diagonalize against a set of all Turing machines. By construction, Turing machine number 1, M1, does not correctly decide the complement of self-accepts because it fails on the input, the encoding of M1. By construction, this is 0, I made it a 1. M2 does not correctly decide the complement of self-accept because it fails on the input, the encoding of M2. Right? And so on. Any Turing machine, M sub I, will fail to decide complement of self-accept because it's going to fail when the input is the encoding of itself. So now, what does that mean? Well, this is, now I'm saying M, the complement of this Turing machine, well, it's a Turing machine, right? So it's a valid Turing machine that I created, and it sits somewhere in this table. I don't know, maybe it's M4. Okay, so I'm going to put it in my table now, this Turing machine, M, the complement of SA. And I can say the same thing. This Turing machine cannot solve the complement of SA because it will fail when the input is the encoding of M complement of SA by construction. Okay, so this Turing machine, in attempting to decide the complement of self-accepts, cannot give the right answer when the input is the complement of M complement of self-accept, this Turing machine. Okay, so this is the tricky part, but hopefully you're following here. And therefore, yeah, we have the conclusion, right? So now for that Turing machine, this statement is independent of ZFC. Okay, so once again, we argued that, look, this is a Turing machine that cannot decide the complement of self-accepts. So there exists some Turing machine input M where it doesn't give the right answer. For that Turing machine M, we first argued that the statement M does not self-accept must be independent. Resolve is going to loop forever. And now we say, okay, for which input does this not give the correct answer when deciding the complement of self-accepts? Well, it's a description of this Turing machine itself as input. It's by construction. Okay, so this is the trickiest part of the lecture. It's a bit mind-bending, but I hope you get the general idea here. Now, by the way, let me ask you this question, and then we'll summarize it. When I run MSA on the input MSA, what does happen? What should I put here? Is it a 0 or a 1 or infinity? It's infinity, right? I mean, we just argued that it doesn't give the correct answer. The only way it's not giving the correct answer is because it's looping forever. So actually, I know this is infinity here. It must be infinity. So indeed, M, the complement of SA, does not self-accept. Indeed, that's the true, because it loops forever. So here's a true statement, which is independent, which is not provable in your formalization. It's independent. Okay, so here's now the summary of this, what we've done. If ZFC is sound, then this statement, M complement SA, given this input, does not accept, is independent of ZFC. Okay, and this is M complement of SA refers to this, which calls this. So let me, compress notation here. So let I denote this statement, MSA does not self-accept. I for independent. So we just showed the following. ZFC is sound implies that I is independent of ZFC. Assuming ZFC is sound, I is independent of ZFC. One observation that we made, by the way, is that we observed that the statement I, that it does not self-accept, is actually true. Right? It loops forever. When you feed MSA its own source code as input, it will loop forever. So the statement is actually true. Assuming ZFC is sound, here's a true statement, I, which cannot be proven. Good. So now I want to do the following. Can we replace ZFC sound with ZFC consistent? Okay, so as I said, soundness implies consistency. So consistency is a weaker assumption. So if I can replace these statements with just the assumption that ZFC is consistent, I prove something stronger. I'm assuming less and getting the same kind of result. And you'll see why this is important. This is going to be important. But this is which brings me to the consistency version. And the consistency version is basically what we had before, exactly the same thing. And you can replace soundness with consistency and get these results. And I'm not going to prove this. It's not too hard to argue. Just trust me that with a bit more work, you can do it. You can do this as well. So theorem, ZFC consistent implies I is independent. And also we observe ZFC consistent implies I is true. Now let's see. Now I treat this as the first independent statement, right? So we basically use diagonalization, and we've constructed an explicit independent statement I, and it's the world's first independent statement, let's say, okay? We did something similar with computation. We argued using diagonalization is that the complement of self-accepts is undecidable. That was the world's first undecidable, explicit undecidable language. And then what did we do? We used reductions to show that other problems are undecidable as well. And so this is something I want to do now is I have the world's first unprovable statement. I want to use reductions in this context, appropriately defined, to prove that other statements must also be undecidable. Let's expand the landscape of unprovability using reductions. So this now brings us to the second incompleteness theorem. Okay, so, and for this I'm going to need a notion of reductions for provability. Okay. So, and it's actually a simple notion. So proving S reduces, I'm going to say proving S reduces to proving T, or that, S reduces to T, if the statement T implies S is provable. Okay? S reduces to T if the statement T implies S is provable. Now, I hope you agree that if S reduces to T, then if T is provable, then S is also going to be provable. Why? Because if S is reduced to T, then I know that this implication is provable. I also am assuming now T is provable. Now, if you tell me T is provable and this implication is provable, then I can conclude S is provable. Okay? If T is provable and T implies S is provable, then S is provable. The thing is, we can use the contrapositive of this. If S is unprovable, then T is unprovable. And I already have one unprovable statement I can use. Okay? So this is the notion of a reduction. And we can use reductions to expand the landscape of unprovability. Okay, so now this brings us now to the second incompleteness theorem. Okay, so I know this statement I is independent, is unprovable. That's what this is the world's first independent statement. Unprovable statement. Now I want to show some other T is unprovable. So I'm going to try to use I as my S here. Is there some statement T such that I reduces to T? If there's a statement T such that I reduces to T, then since I is unprovable, T is also going to be unprovable. So my question now to you is this. Is there any T that you know such that I reduces to T, which means what? It means that T implies I is provable. Is there any T such that, any statement such that T implies I is provable? Is there any statement such that that we know that T implies I? Yeah. It's right on the board. ZFC consistent implies I. At least I know, let's take this to be your T. T implies I is something that we proved. Right? So we have this theorem. ZFC consistent implies I. And is it provable? Is this statement provable? Well, we just proved it, right? I mean, I proved it to you. I mean, not the consistency version, but modulo that detail. I told you, like, there exists a Gorm proof of the theorem. We went through it. We went through the soundness version, but assume we went through the consistency version. And by Gorm to ZFC thesis, there exists ZFC proof of the theorem as well. So the statement that we Gorm proved by Gorm to ZFC thesis has also a ZFC proof. So this is provable. So what's the conclusion? So T is unprovable. And this is the second incompleteness theorem. If ZFC is consistent, the statement ZFC consistent is not provable. ZFC cannot prove its own consistency. Okay? So the bottom line is that not only there is an independent statement, and not only there is incompleteness, the consistency of the system is an explicit, unprovable statement. Recall, this is Hilbert's program. Hilbert wanted, give me a formalization of good old regular mathematics, prove to me it's complete. So he wanted every statement, for every statement S or negation of S is provable, and also prove that it's consistent, right? And Godel said, you know what? It's not going to be complete. There is going to be independent stuff. And not only that, the consistency of the system is one of these things you cannot prove. Right? So this was a knockout punch to Hilbert's dream. In fact, Hilbert, wanted also that is provable is decidable. So it could still be the case, even though you have incompleteness, it could still be the case that is provable is decidable, and there's a mechanical procedure for this. And actually, Alan Turing showed that this is undecidable. Okay, so this is basically part 1 of 251. So we saw the foundations of mathematics, birth of computer science, formalizing computation. And then we saw this chain of ideas, uncountability. The work of Cantor led to uncomputability, which led to unprovability. And you might ask now, what's going to happen next, right? Well, okay, so we said you can prove, like, the halting problem is undecidable, Entscheidungsproblem is undecidable, uncomputable. On the other hand, here's like modifications of these things, like slightly massaging the problem. What if I add the parameter k to these things, and I said, look, does m of x halt within k steps? Or, does the statement S have a proof using at most k symbols? Now these are decidable, right? So these are computable, these are decidable. So the computability versus uncomputability was not in some sense, the main question. The main question is, because I can always create computable problems like this, the main question is, well, can we still solve these? Okay, we can solve these, but can these be solved efficiently? Right? Are they practically computable? They're computable, but what matters to us is, are they practically computable or not? And that now question leads us to the next part, time complexity, complexity theory. And the highlight in this part is going to be the famous P versus NP problem. Okay.